Right, good evening everyone. We're kicking off with our SIMI live stream in which we're going to be looking at paper 2. Before we dive into the technicalities of the paper, let's just quickly talk about a couple of things. Firstly, SIMI, the Shai Zibalo Maths Institute, is run by myself and my sister Ruth, and we are committed to trying to make an improvement to maths in South Africa. So please like, share, subscribe, all those good things on our social media platforms as shown on the screen. And we're going to dive in first and start off by just looking at some sort of general tips that we feel be useful. Right, the first thing is that use the reading time, right, to identify questions you know you can do, right? And if you make a start with those questions, then you're going to build your confidence. A really, really big idea is to remain calm at all times. If you're unable to do something, don't get stressed, move on and find something that you can do. Don't get stuck on a question and waste time, and just breathe. Breathe deep and slow. It helps keep you calm, all right? And when we're calm, we think better. Okay, obviously you need to try and show your working and communicate your thinking. And a really big part of that is giving reasons, obviously, especially in circle geometry, but also sometimes in other areas as well. Right, a big idea, and we'll talk about it as we go through, but let's suppose you can't do part A of a geometry question and it's asked you to prove two lines parallel. From then onwards, you can use the fact that those lines are parallel without any further penalty, right? And you're going to need to do that. Right, the way geometry tends to work is it tends to progress from one topic to the one, it builds, in other words. So in other words, part C of the question actually uses what you've just done in part B and in part A. Right, try and train yourself to ask yourself, what's special in this diagram, okay? And then obviously it goes without saying that attempt every question. Don't leave anything blank. You can't get any marks for a blank screen, a blank page. All right. See what you can do, even if it's the most basic of things. Okay. Right. So we're going to dive in and we're going to be looking at this paper. It's actually a past DBE exam, all right, from a couple of years ago. And this first question talks about a matric class which had to vote for the chairperson of the Council of Learners. And there's a scatter plot which shows the IQ of the 10 learners who received the most votes and the number of votes that they received. So for example, this person over here, high IQ and quite a high number of votes. Right. Okay. So, sorry, that didn't go quite as planned. Sorry. Right. Let's get back to that. Apologies. Okay. So what also happened is before the election, the popularity of each of these 10 learners was established and a popularity score was assigned to each. And then we've got a table here of popularity score versus number of votes. Okay, and the first thing we are asked to do is calculate the mean number of votes that these 10 learners received. Okay, so what we are able to do is we're able to put this data into our calculator, right, and we can put it in right away in shift mode, and we're going to go for sorry, not shift mode, we're going to go mode, and we're going to go for stat mode, and we're going to go for two variable stats. And the reason being is that just now we're going to be asked to kind of give least squares, regression lines, etc. So we're going to go for option 2, which is a plus bx. Right, we're going to put in all these x data points first. So 32, 89, 35, 82, 50, 59, 81, 40, 79, and 65. All right, now we're going to go back up to the top and we're going to put in the y values, the corresponding y values. So 9, 22, 10, 21, 11, 15, 20, 12, 19, and 16. Okay, at this point we press all clear, which I know sounds like a fairly strange thing to do, but we're going to do that anyway. And now what we're going to do is we are going to go shift stat, and we're going to get the variables for this data, and we're going to get the mean number of votes. Now remember that's y, so we're going to go for option 5, y bar. All right, and we get 15,5. Okay, so y bar equals 15,5. It's really important that we take care putting those numbers into our calculator. Make sure that we get them exactly right. Then we want the standard deviation of the number of votes, which is obviously the standard deviation of the y values. So we're going to go shift stat 4 for the variables and 5 for the standard deviation of the y values. Okay, so I've gone for the mean again. Shift stat 4, and so then it's option 6 for the standard deviation of the y values. My apologies. And we get 4,59 if we round off to 2 decimal places. 4,59. Okay, so that's the standard deviation of the y values. Okay, the learners who received fewer votes than 1 standard deviation below the mean were not invited for an interview. Okay, so what we're going to do now is we're going to take this value of 15,5. We're going to subtract a standard deviation, which is 4,59, and we get a kind of a cutoff, if we like, of 10,91. So the learners who will be invited for an interview are the ones that got more than 10,9. All right, and so there are 8 of them, I think. Yeah, we just got to count the ones that got more than 10,9. It's 1, 2, 3, 4, 5, 6, 7, 8. Right, so 8. Okay. Then we're going to talk briefly now about least squares regression lines. Before we try to answer the question around the least squares regression line, let's just talk a little bit about how these things work. Okay, so the first thing is that a least squares regression line is basically a kind of a line of best fit, all right? And so here we've got some dots, we've got some blue dots, we've actually got one red dot as well, and there's a reason for that, which we'll get into just now, all right? But if we show the line of best fit, there it is, okay? And it's got an equation over there. Okay, now we can also calculate a correlation coefficient. Just want to look at what is the effect of this red dot. All right, this red dot we could describe as a kind of an outlier. All right, it's quite sort of different to the rest of the data. Okay, and maybe in fact it's even the whole way down there. All right, if we calculate the correlation coefficient, and remember the correlation coefficient, the closer it is to 1 or minus 1, the stronger the correlation. Okay, so the correlation coefficient of all those points is actually 0.29. If we remove the red dot, will our correlation get stronger or weaker? And the answer is it'll definitely get stronger, and it'll get closer to positive 1. Okay, and it's actually 0.95. The blue dots are actually very strongly correlated. Okay, what will happen if we remove the red dot? What will happen to the gradient of this line? All right, and I want you to think almost that this red dot is almost pulling the red line down. And so if we remove the red dot and we show the line of best fit without the red data point, the line will actually get steeper. Okay, right, so that's a kind of a conceptual understanding idea. All right, you can see it's now got a gradient of 0.6. Okay, the next thing we want to look at is just the whole idea of correlation coefficients. Okay, so what we've got over here is we've got a whole lot of dots, and we've got a little app running here whereby we are able to kind of take a guess at the correlation. Now, I would suggest that this is a very low correlation. I'm going to take a guess here of 0, okay? And I'm going to ask the software to show the correlation. Okay, it's actually negative 0.12. I think that's quite tough to actually see that maybe. let's do another one. This one's definitely positive, and this data is reasonably strongly correlated. I'm going to go with 0.6. Okay, and in fact it was 0.61. Let's just do one more. All right, that's definitely negatively correlated, but not very strongly. I would say negative 0.4 perhaps. Oh, sorry, 0.4. Let's have a look. Okay, all right, we'll do one more. Just let's just see if we can get a okay. That one there, positive or negative. All right, definitely negative. Remember the correlation coefficient R and the gradient B have the same sign. Right, so this is a negative correlation, and this is actually, I think, quite strong. I'm going to go with 0.8. Sorry, 0.8, not comma 8. All right, it's actually even stronger still. It's negative 0.9. Okay, all right, so now let's dive in and let's work out the equation of the least squares regression line. Okay, so we've got this data into our calculator, and all we're going to do is we're going to go shift stat. This time we're going to go for option 5, which is regression, and we're going to get our A value and our B value. So 1, all right, 1,77, all right, 1,771 is our A value, and now we do exactly the same. We go shift stat 5, and we'll get our B value. Don't forget to press equals, and we get 0.2243. Okay, right, so our actual equation of our line of best fit, our least squares regression line is what it's called, is y equals 0,2243x plus 1,771. Okay, and that's our equation. Right, notice that there's 3 marks, and the real reason for that is the time taken to put the thing into the calculator. Predict the number of votes that a learner with a popularity score of 72 will receive. Well, all we're going to do is we're going to sub 72 in here. So we're going to go y equals 0,2243 times 72 plus 1,771. I'm just going to show you how you can actually do that directly on your calculator. All right. So what you can do is you can put in the value that we want to predict. So you go 72, and then you go shift stat 5, and you choose option 5. In other words, get the y value for that x value. And we get 17,92. Obviously, that's number of votes, so we'd round it up to 18 votes. Okay. Then it says, using the scatter plot and the table above, provide a reason why IQ is not a good indicator of the number of votes that a learner could receive. Let's go and look at that scatter plot again. There's basically no relationship. There's no correlation. Okay, we're not expected to put this into our calculator and work out a correlation. We just need to say there's very little, you can almost say there's no relationship, no real relationship between IQ and votes. Okay, then the next one says, what about the prediction in question 1.4 is reliable, right? Okay, so there are 2 things about this. Firstly, what's the strength of the relationship? Okay, and and we can get that, all right? Let's get the correlation coefficient. Shift stat 5, and we're going to go for option 3, and we get a correlation of 0.98. That is a very, very strong relationship. Okay, yes, okay, since R, R is almost 1, approximately 1, okay, the relationship is very strong. There is another thing which is actually interestingly not mentioned on the official memo, and that is that the x value that we're using, right, is within the data range. So we're checking out 72, a popularity score of 72. Now, if we look at the popularity scores, there are some that are bigger than 72 and there's some that are smaller. In other words, we are interpolating, okay, or we are not extrapolating. Remember, extrapolation is a dicey thing when you look outside of the range of the original data. Okay, so both of those things I think are quite important there, even though it's only 1 mark. Right, the next question has got an ogive curve, all right, and there's the cumulative frequency on the vertical axis and the percentage of salary that employees spent on fuel. Okay, first question says, how many employees are there in the company? Well, we're basically going to look at where the graph maxes out, and it maxes out at 60. Write down the modal class. Now the modal class is going to be the class that's got the most people in. So what we want to look is in which interval did the graph grow upwards the most. In other words, where does it go upwards the most steeply? And that's between 20 and 25%. So that's our modal class. How many employees spent more than 22.5% of their monthly salary on fuel? Well, 22.5% is over here. All right, and up to there, we've got 34. All right, so that's up that there's 34. 34. And so, in fact, 26 spent more than that. The next question says, an employee spent 2,400 Rand of his salary on fuel, all right? And then it says, what's the salary if that is equating to 7%? So this is not really a statistics question at all. This is just a basic proportion question. So we know that 7% is equivalent to 2,400 Rand. All right, and we want to find out what 100% is. Now remember, with kind of equivalence relationships, we can we can multiply both sides by a certain number, or we can divide by a certain number. We cannot add. So if we divide both sides here by 7, all right, we will get what 1% is. Okay, so 1% will be 2,400 divided by 7. How do we get from 1% to 100%? Well, that's fairly obvious, isn't it? We're going to multiply on both sides by 100. Okay, and when we work this out on a calculator, we actually get 34,285 and 71 cents. Okay. The monthly salaries of these employees remains constant, and the number of litres of fuel used in each month also remains constant. If the fuel price increases, all right, how will the above ogive curve change? All right, and if we just go and look at this curve, basically, all right, everyone's actually going to spend slightly more. Right, so the graph will actually move slightly to the right, and it'll become steeper at the end. Okay, so we just need to write that down. So the curve will shift right. Curve shifts right and becomes steeper. Okay. All right, and that is the end of the data handling, I think. Yes, it is. Okay, the next, and in these exams, in the department exams, the topics are, as you know, they're separated out. Next up, we're going to look at analytical geometry, right? Before we do, just two things I want to quickly remind you about. And they've got to do with angle of inclination, right? Because I think it's the one aspect that's not always necessarily very well understood. So let's take a look at angle of inclination. Just two little kind of sketches to help us understand. The first is that the angle of inclination of a line, all right, is how much it's tilting up from kind of 3 o'clock on the clock face, or east if you like. All right, so they're kind of 20 degrees, okay? But what I want to show you here is that, so there now the angle of inclination is 58 degrees, now maybe it's 118 degrees. You might be saying, well, can we have like a 200-degree angle of inclination? And the answer is no. Once it goes past 180, it's going uphill again. All right, so the important idea here is that our angle of inclination, all right, is a quadrant 1 or a quadrant 2 angle. Those are the only two options for an angle of inclination. Okay, right. Next up, so I see that that kind of fell off the screen a little bit, but quadrant 1 or quadrant 2. Okay, next up we're going to look at actually calculating the angle of inclination, and we're going to have a look at this diagram over here. All right, we know that the gradient of the angle of inclination is the same as the tan, sorry, the gradient of the line is the same as the tan of the angle of inclination. Right, so let's see if we can work out this line's angle of inclination. Okay, and the first point we want to make is that if we put a horizontal line in, it doesn't actually matter where this horizontal line is, okay, because the angle of inclination will be kind of in here, and it'll be the same size because these are all corresponding angles. Okay, all right. So what's the gradient of this line? Well, we are rising 5 and we're running across 3. So the gradient of the line is actually 5 over 3. Okay, it's 1,67. Okay, now let's pull up a calculator and let's see what the angle of inclination is going to be. Let's get out of stat mode. All right, and we're going to go shift tan of 5 over 3. Remember we said our gradient is 5 over 3. 5 over 3. Okay, and we get about 59 degrees. Okay, and let's suss that out, because if we show the angle of inclination, there it is. Okay, 59,04 degrees. Okay, so that's the one kind of thing we can do here. Let's move some things around. Let's move that point to there, and let's move that point to there. All right, in fact, not quite to there. Let's go to there. Okay, let's work out the angle of inclination now. And remember, this angle of inclination is going to be a quadrant 2 angle. Okay, so we're going to get the gradient. All right, this line is dropping 4 in the time that it runs across 5. So it's got a gradient of negative 0,8. All right, there's the gradient. Okay, now what I like to do on my calculator, I would find what I would call a key angle. I would go shift tan of 0.8. Okay, and we in fact get about 38,7 degrees. Now that is clearly not the answer. That is how much I want to be in quadrant 2 by. So I'm going to go 180 minus that value. 180 minus my answer, and we get 141,3. Right, and if we go and have a look at our angle of inclination, there it is. Okay, now you might say, well, I've done that different. We don't do it like that. I wasn't taught that. All right. You might say, I'm going to put the negative into the calculator. Right. And if you put the negative into the calculator, then you're going to get shift tan of negative 0.8. All right. And we're going to get a negative answer here. Okay. We actually get negative 38,7. All right. And that, in fact, is this angle kind of below the x-axis. So we would have to add 180 to get that answer. The same answer as before. Okay. All right. Okay, right, I think we seem to have lost our calculator there. Okay, not sure why that is. Okay, just the last one on this, and that is that obviously if we've got an angle of inclination, and maybe we don't know the names of these points, all right, so we don't know the names of these points, we can easily get the gradient if we know the angle of inclination, right, just by finding the tan of that angle. So in this case, the tan of 38,68. So my calculator doesn't seem to be showing on the screen anymore. I'm not sure why. Tan of 38,68, and we get a gradient of 0.8. Right, and let's ask the software to show us the gradient, and there it is. Okay, right. I hope both of those were kind of useful, and now we're going to go back and start solving our analytical geometry questions. Okay. Right, so we've got a diagram over here, and there's a whole lot of sort of stuff going on. What we are told is the equation of line AC. This line has an equation of 5x minus 6y equals 8. Okay, don't think there's much else. We have got some parallel lines here that we need to be aware of. I think and we've got some equal lines here. Right. So the first thing it says is, what's the gradient of AB? Right. Well, that's pretty straightforward. You can use your formula where you're going to go y value minus y value over x value minus x value. But in fact, we are dropping down 6. That's our y value is dropping by 6, negative 6. And our x value is growing. We're always running from left to right. Our x value is growing by 2. So the answer, negative 3. Next up, we asked for the size of alpha. And this is exactly what we've just been kind of dealing with. All right. The calculator seems to be back, which is a relief. Okay, so I would go shift tan of 3. All right. That's clearly not the size of alpha. That is, in fact, the size of this angle in here. All right. So now what we would do is we would go 180 minus that answer. And we get 108,4 degrees. 108,43 degrees. Okay. The next question asks us to find the coordinates of t. Now, t is just the midpoint of those 2 points. And again, you can use your formula. The formula says you just average the x values. Okay. I actually prefer, and this method is sort of more generally useful if you wanted to go a third of the way along the line, for example, rather than the midpoint. I say to myself, how far have we moved when we go from -2 to 6? Well, it's actually 8. And what's half of 8? Half of 8 is 4. So I could either add 4 to -2, or in fact I could subtract 4 from 6 and I get to the same place. The y value is dropping from -3 to -4, all right? So it's going down by 1, so the midpoint must be going down by a half. So in other words, -3,5. All right, so there's the coordinates of t, 2 and -3,5. The coordinates of s, all right, s is obviously, I say obviously, s is a significant point, all right? It's on the y-axis, which means it must have an x value of 0. Okay, so, but we also know that it's on this line AC. So if in our equation 5x minus y equals 8, we let x be 0, 5x minus y, sorry, 5x minus 6y equals 8. We're going to let x be 0. We get -6y equals 8. right? So in fact, y is negative 8 over 6 or negative 4 over 3. Okay, now just be careful. They want the coordinates of, sorry, this is coordinates of S, all right? And obviously the x value is 0 and the y value negative 4 over 3. Okay, the next question asks us to find the equation of CD, all right, in standard form, CD. Now, if we look at CD, it's actually parallel to AB. And we've worked out the gradient of AB. We know the gradient of AB is minus 3. So this line must also have a gradient of minus 3, but it goes through the points negative 2, negative 3. So we're going to use our y equals mx plus c formula with a gradient of minus 3 and passing through negative 2, negative 3. So the line looks something like this. M equals negative 3, but this point, negative 2, negative 3 is on that line. We've got choices here. There's two formulas for a straight line. We could either use y equals mx plus c, or y minus the y value, so it'll actually be y plus 3, is the gradient times x minus the x value, so it'll actually be x plus 2. We end up, if we simplify this, we get negative 3x, we get negative 6 minus another 3 minus 9. Okay, and that's the equation of the line CD in the right form. Next question asks us to find the size of DCA. All right, now DCA is this angle over here. Okay, we're trying to find the size of this angle over here. And this looks a little messy, okay? I think there are two ways we can do this, all right? What we can do, and I'm not going to actually close it out because I don't think it's the best way, we can put in a horizontal line here, okay? And because we've got a horizontal line, okay, it doesn't look entirely horizontal, but we know the gradient of this line, we could work out using our tan of the angle. Okay, we could work out the size of this angle over here. All right, what I'm calling angle alpha. I'm going to highlight it with a green pen. All right, we could also, because we know the size of this gradient, we could work out the size of this angle beta. Okay, and obviously if we subtracted, okay, if we worked out beta, worked out alpha, and subtracted them, we'd have the angle that we look at. All right, I think there's a slightly easier way of doing it, and that is to, and I'm going to take all of this out, that's to realize that in fact this angle that they are asking us to find is actually an alternate angle with this angle. And maybe this angle will actually be easier to find. Bearing in mind that we've already found alpha, okay, we know, and let's just remind ourselves, alpha is 108,43. And this angle, or rather alpha, is actually an exterior angle of this triangle. So in other words, if I can work out this angle, AFR, okay, then I can easily get my answer for the size of this angle. I'm going to write everything here up at the top here. So in other words, we're answering now question 3.3.1, and we're going to answer it up here. Just so we've got the sketch in front of us. Okay, so the first thing is that DCA is actually going to be equal to FAR. All right, and the reason for that is alternate angles with the line DC parallel to AB. Okay, so that's the first thing. Now, this line over here, all right, can be rearranged, 5x minus 6y equals 8, can be rearranged to 5x minus 8 equals 6y. We add 6y to both sides. And now if we divide by 6 on both sides, we get 5/6 of x minus 8/6. Okay, 8/6 is actually 4/3. The most important thing here is not so much the equation of the line, just the gradient. All right, so that's the gradient of that line. So if we give this little angle a name, and let's call this beta. All right, we now know that the tan of beta is going to be 5/6. Okay, so we can get beta easily by undoing tan of 5/6 on our calculator. Shift tan of 5/6, and we get 39,81. Right, and then lastly, angle FAR will just be 108,43 minus 39,81. All right, and that is going to equal 108,43 minus the previous answer, and we get 68,63 degrees. Okay, 68,63 if we use full accuracy, 68,63 degrees. Okay, and that's actually what DCA equals. Okay, right, now the last question, and this is lucky it's the last one because it's getting a little bit messy, the area of POSC. So what we're looking for now, we're looking for in fact the area of this kind of rather odd looking shape here, this pink shape. And I want to go back to something I said right in the beginning, is that these questions tend to build on one another. All right, we previously worked out the coordinates of point S. And so that point there is -4/3. Okay, now, if we look at this picture, okay, we could work out the area of the triangle, okay. Yeah, I think possibly we want to work out the area of triangle PFC, all right, and then take off the area of triangle OFS. Okay, and this is a classic place where we can really try and just show our working, all right. So again, things are a little bit tight here, but basically we know the size of this angle, okay. We know that this is 68,63. So can we work out the area of this whole triangle? Yes, we can, because we can work out the coordinates of point F. All right, point F we can work out by letting y be 0 in this equation. All right, and so we actually get x to be 8/5. Can we work out the equation of point P? Yes, we can. All right, because point P, just looking if we need point P, did we work out the equation of CD? Yes, we did work out the equation of CD. It was -3x minus 9. All right, so in fact, this point over here, all right, is -3. Okay, because we know the equation of this line is y equals negative 3x minus 9. So we can easily work out its x-intercept by letting y be 0. Okay, so that's negative 3. All right, now it's actually now fairly straightforward to work out the area of triangle PFC. Okay, so our area that we've tried to find, okay, the area of POSC is going to be the area of triangle PFC minus the area of triangle, this little triangle, this little white triangle on the side here, OFS. Okay, and PFC, we can use our area rule, all right, because it's going to be half the length of PC, all right, so half PC times the length of FC minus, all right, the area of triangle OFS. Now OFS is a right angle triangle, so we can use half base times height. So this is just going to be half 8/5 and 4/3, because that length there is going to be 4/3. Okay, and sorry, and obviously also in here, I'm using the area rule, I need the sine of my angle of 68,63. Okay, so now it's just a question of using my distance formula, okay, and I am going to, at this point, I'm going to just write down the final answer for us. The final answer comes to 5,83 units squared. Right, obviously what I need to do there is I need to use the distance formula to find the length of PC and also of FC. Okay, right, but I think it's getting a little bit cluttered there. Okay, it is one of the challenges of trying to do these things online with one board. Okay, let's look at question 4, right? And what it tells us up front is that the point M is the center of the circle, okay? And it also tells us that PN is the diameter, and that KL is the tangent, okay, at that point. All right, so the first thing it says, what's the coordinates of P? Okay, and again, I'm going to show you two ways of doing this. The way I kind of prefer to do it is to say to ourselves, well, when we moved from N to M, what happened to my X value? Well, it dropped by 4. Because we're going to move the same distance again, it must drop by another 4. So P must be -1, all right? And let's look at what the Y value's done. It's dropped by 3. It must drop by another 3. So -1, -8. That's how I would do it. Again, I just write the answer down. Okay. If you want to use your midpoint formula, you could let P be the point XY. Okay. And then remember that X plus 7 over 2 must give us the X value of this midpoint. In other words, must give us 3. Now we've got an equation with only one variable, and we can solve for that. And we multiply both sides by 2, we get X plus 7 equals 6. Subtract 7 from both sides, we get X equals -1. All right, we do exactly the same with the Y values. Okay, in other words, Y plus -2 or Y minus 2 over 2 must equal 3. Multiply both sides by 2 to get Y minus 2 equals 8. Doesn't equal 8 at all. Y minus 2 equals 6. And then add 2 to both sides, and now we get 8. All right, don't forget, all this work, we've still got to actually make sure that we write down the coordinates. So we'd write down P is -1, 8. Okay, actually a whole lot easier to do it just sort of visually, but you choose the method you prefer. Right, now they want us to write down the equation of this circle in standard form. And remember, this is x minus the x coordinate of the center. So it's just going to be x minus, all right, x minus 3 all squared, y minus the y value, so y plus 5 all squared, equals the radius squared. Okay, so what we're going to have to do now is we have to work out mn. Okay, and let's just work that out over here. Remember, n is 7, negative 2. M is 3, negative 5. 3, negative 5, and 7, negative 2. Just going to do this fairly slowly because we didn't practice the distance formula in the previous example. So this line is going to be our radius. Okay, and remember our distance formula says r equals the square root, okay, of the x values subtracted and squared, 7 minus 3 all squared, minus 2 minus minus 5, or minus 2 plus 5 all squared. Okay, and so this becomes 4, which is 16. This becomes 3. When we square it, we get 9. So we get the square root of 25. Okay, so in fact, r is actually 5. But remember in our equation here, we don't want r, we actually want r squared. So there's our final answer for the equation of the circle. Okay. Right, next up, they ask us to find the equation of KL. Right, now KL is the equation of the tangent. Okay, and this is a very, very standard idea. I'm going to write this answer kind of up here. So this is the answer for 4.2.2, just so we can see what we're doing. All right, the first thing we're going to observe is that this is a right angle. Okay, so we can work out the gradient of mn, m of mn. We're rising 3 and we're running across 4. So therefore the gradient of KL will be negative 4 over 3. All right, and we can just write radius perpendicular to tangent. All right, we need to write that. We need to explain how we've worked out that gradient of KL. The last thing we need to do is to find the equation of KL using this gradient and this point 7, negative 2. So y minus minus 2, all right? In fact, I used this method last time, and I suspect more of you are using y equals mx plus c. So I'll use y equals mx plus c. Y equals mx plus c. Let's put in the point. Negative 2 is the y value. Negative 4 over 3 is the gradient. All right. 7 is the x value plus c. C is the only variable. So we get negative 2 equals negative 28 over 3 plus c. Let's add 28 over 3 to both sides, bearing in mind that negative 2 is actually 6 over 3. All right, so it's negative 6 over 3 plus 28 over 3. We actually get that c is 22 over 3. And we get our final answer for the equation of the tangent to be negative 4 over 3x plus 22 over 3. Okay. That's a very, very standard question type. Okay. Right, then they ask us for which values will, now this line notices the same gradient, okay, and it's just a line that's going to kind of sort of move up and down. For which values will this be a secant? Okay, now a secant, and I hope you know what a secant is. A secant, so here's the tangent. Okay, a secant is going to cut the circle twice. So in other words, if we move this line, do you agree? Now it will be a secant. It will be a secant over there. It will still be a secant over there. All right, and it will be a secant down to there. So what we would need to do is work out the equation of the tangent at P. All right? And so let's do that. Let's work out the equation of the tangent at P. Okay. All right. And very similar exercise. Okay. We're now doing question 4.3. Okay. So the equation of, I'm just going to sort of draw it in here. Okay, so the equation of this tangent, and these lines are meant to be parallel, I don't know if I've drawn that very well, but the equation of this line here is, remember we worked out the coordinates of P. It's right there, it's -1, -8. Okay, so this line has actually just got an equation of y plus 8, I'm doing my y minus a y value version again, equals the gradient, -4/3, x minus the x value, so in other words x plus 1. This simplifies to, all right, -4/3x, and this time -28/3. Okay, so that's the position, all right, that's the equation that we get for the red line, okay, and this, we've got the equation for the orange line written in blue here. Okay, so if our C values, in other words our K value in the question, is in between those two numbers, all right, then we will get a secant. That line will hit the circle twice. Okay, so that all summarizes to, okay, K must be less than the first y-intercept and bigger than the next one. All right, and this is actually 10. No, it's not. It's definitely not 10. This is 9. All right, 3 goes into 22. In fact, it's 7 and 1/3. All right, and this is -9 and 1/3. Okay, I just want to draw a little picture for you, just show you a kind of sketch here of what's actually going on. All right, and there it is. Okay, and I'm going to find it on my other screen here, but there it is. And if I show the secant, all right, and you'll see there is 7 1/3. Okay, as long as K is less than 7 1/3, this line slides down like this, and it can go as basically down to -9 1/3, but we need to be just slightly bigger than -9 1/3 in order for it to be a secant. Okay, so hopefully that gives us a nice kind of visual of what's going on here. Right. Okay. Okay, now let's look at this question. Right. And we don't actually need to refer to our diagram here. It basically talks about another point A, which is it's got the same x and y values, and B, which are not shown on the diagram. From point A, another tangent is drawn to touch the circle with center M at B. Show that the length of the tangent is given by that. Okay, so let's just try and draw a little picture here. So basically we've got a circle. Okay, we're definitely not winning with drawing a circle there. Let's have another go. Okay, we know the center of the circle, remember, okay, is 3, -5. Then we've got a point up here, all right, which is point A, which has x value t and y value t, and we've got a tangent drawn from that point to the circle. Okay, and we want to work out the length of the tangent. Now you might say, Paul, isn't there another tangent down here? Okay, and you'd be absolutely right, but they will have the same length. Okay, so we don't need to worry about which one we're finding. Okay, we're just going to find the equation of this one. This is going to hit the circle at B. Okay, now we don't know kind of much about that, all right, but we can get an expression for the length of the tangent, and the reason we can is, once again, because if we draw this in, we know that there's a right angle in here. Okay, so we know this is the radius, and we worked it out to be 5. We don't know this point, but in fact we don't need to know this point. What we do need to show is that we know that this is a right angle. Okay, so I'm just going to draw a nice big right angle in here. Sorry, looking for a different color pen. Here we go. Okay, sorry. There it is. Okay, and we can work out AM, this is M, easily enough. All right, and then we can use Pythagoras to get AB. Okay, so in fact AB squared will be AM squared minus 5 squared. Okay, and AM squared is just going to be 3 minus T all squared. Okay, we're just using that point and that point, and then minus 5 minus T all squared. I'm just using my distance formula, but I'm not square rooting it because I actually want the squares of these distances. And there's minus 5 squared, that's the radius squared. So that'll give me AB squared. All right, now, just to save a little bit of time, we're going to do this quite quickly. This is going to be 9 minus 6T plus T squared plus 25 minus, or plus 10T, but doubled, so plus 20T. All right, and then plus T squared and minus 25. Okay, so these obviously cancel out. Okay, and we end up with negative 6T plus 20T, right, which is going to be 14T. Okay, and somewhere we've made a bit of a hash here. It's plus 20T. Okay, we've got 9, which is good. We've got T squared and T squared, which is good. I've got minus 6T and I've got plus 20. Sorry, this is not plus 20T. This is plus 10T. All right, my apologies. Okay, doubled it twice. Okay, plus 10T. So we end up with the square root. Okay, for AB squared will be 2T squared and then plus 4T plus 9. Okay, so AB is going to be the square root of that. Okay, so we've established that result. Then it says determine the minimum length of AB, and this is actually quite nice, all right, because what we've got AB is the square root of 2T squared plus 4T plus 9. Okay, and we want to make this here as small as possible. Okay, there are two ways of doing this. One is to use calculus, right? And so we could say, let's differentiate with respect to t, 2t squared plus 4t plus 9, and make that equal to 0, right? Because we want the smallest possible value, and so we get 4t plus 4. Sorry, 4t plus 4 is 0. So t is in fact negative 1. Okay. And obviously if t is -1, all right, then we could work out the length of AB, all right, by putting -1 in here. And when we do that, all right, we get 2 minus 4, which is -2, plus 9, which is 7. So AB is equal to the square root of 7. That is one way of doing it. All right, the square root of 7 is about 2,65. Okay, another way of doing it, which in some ways is more elegant, but maybe a little bit harder work, is to try and complete the square on this thing inside here. Okay, and so I'm going to take out the 2, and we're going to get t squared plus 2t, okay, plus 9 over 2. Now we are going to try and complete the square with the t squared piece. Okay, so it's obviously going to be t plus 1 all squared. All right, we've added in here, okay, we've added in a 1 that wasn't there, so we need to subtract a 1. So our 9 over 2, which is 4.5, we need to subtract a 1. Okay, and if I tidy this up, I actually get the square root of 2 lots of t plus 1 all squared. Now this was 7 over 2, and when we multiply the 2 back in, we get 7. Right, and what we can see looking at this is that this will have a minimum length when t equals a minimum of 7, okay, but remember it's underneath the root sign, so the minimum of square root of 7 when t equals -1. Okay, and I just want to show you a little picture of this as well. Okay, so we've got this diagram over here. All right, and we've got, I can just find this picture on my screen. There it is over there. And notice, I remember I said the minimum length would be about 2,65, and the value of t, of the coordinates of point A, would be at -1. And you can see that red line's getting shorter and shorter, okay? And when we get to about -1, okay, I've gone just past -1, but we can see that our length is now at a minimum. Okay, when I start going past -1, the length gets longer again. Okay, so longer and shorter. Okay. Right, we're going on to trigonometry, so our third topic. Okay, before we do, I want to just give you a quick reminder, just some sort of background info on trig. Okay, so right, just a reminder of kind of the basics of trig. Basically what happens here is that we measure angles from kind of 3 o'clock or east going anti-clockwise. So there's a 30-degree angle. There are 3 lengths attached to this angle. There's the x value of the point, the y value of the point, and r. We can work out our trig ratios, and we know that sine of 30 is a half. It's 4 over 8. Notice if I make the circle bigger, all right, the values change, but the sine of 30 is always a half. Right, and the reason being is that these triangles that you can see forming inside here, inside the circle, are all similar. So the ratios of the sides are the same. Okay, right. Now, just a quick reminder of how our reductions form. Okay, if we show another angle, and if we are that same amount as the green angle off a horizontal axis, notice that the values on the point Q are exactly the same numbers, maybe different signs, as on point P. And that means that our red trig ratios would have exactly the same size. So in other words, if we at 30 or 180 minus 30, we get the same numbers here. Maybe not the same signs, but the same numbers. If we go 180 plus 30, we once again get those same numbers. And if we go 360 minus 30, we once again get those same numbers. Okay. Remember, though, that if we go 90 plus 30, something else happens, all right? And what actually happens, you'll see that now the x and y values on the point Q are swapped around from the point P. And so sine has the same value, not necessarily the same sign, but the same value as cos of 120, sine of 30. Sine of 120, cos of 30. So the upshot of all of that is that when we deviate off a horizontal axis, our ratio stays the same, and we get the sine from the cast diagram. And when we deviate off a vertical axis, all right, we change to our co-ratio. Okay, let's dive in and let's look at the questions that we're going to answer here. Right, so we get told that we've got a situation here where we are in between 90 and 270. So we are either in quadrant 2 or 3. If we had to draw our sort of little cast diagram, we basically are in quadrant 2 or quadrant 3. Okay. However, we know that root 13 sine x plus 3 equals 0. If we just solve that little equation, we actually know that sine x is negative 3 over root 13. Okay, and which quadrant must we be in? If we in either quadrant 2 or 3, but sine's negative, right, we're definitely in this quadrant over here. Okay, right, so next up we get asked to find the sine of 360 plus x. Now the sine of 360 plus x will be in exactly the same place. So it will just be, this is plus 3, yeah, so it's minus 3. So sine of 360 plus x will be exactly the same. It will also equal negative 3 over root 13. Okay. Right. Okay, then tan x. Okay, what we're going to need for tan x is a kind of a little picture for ourselves. Okay, and remember that if we've got sine x equals negative root 3 over 13, okay, our little picture basically, just thinking as a key angle in the first quadrant, sine is our y value over our r value. Okay, and so we actually get a value of 2 over here, and so tan of x, all right, will be y over x. It will be 3 over 2, all right, but remember we're in quadrant 3, so it will be negative 3 over 2. Cos of 180 plus x, using our reduction formula, we're in quadrant 3, or for horizontal axis, that will be the negative of cos of x. All right, and cos of x, remember x is a third quadrant angle, okay, so cos of x would be negative anyway, and it would be the negative of 2 over root 13, so now it would be the negative of negative 2 over root 13. It would in fact be positive 2 over root 13. If we put that into a calculator, it will rationalize the denominator for us, and we get 2 root 13 over 13. Okay. Right, the next question is a typical kind of reduction formula type thing. Okay, remember this, and remember that when we deviate off a vertical axis, 90 degrees, okay, we must change to a co-ratio. So cos of 90 plus theta, we're in quadrant 2, cos is negative in quadrant 2, we go negative sine theta. Sine of theta minus 180, all right? The easiest thing to do here is to add 360. Because remember, if we add 360, we end up in exactly the same place. If we add 360, we actually get sine of 180 plus theta. And that's more easy to visualize. And this is 3 lots of sine of minus theta. Sine of minus theta is just theta degrees away from the horizontal axis. So we're in quadrant 4 because we're going clockwise, minus theta. So this is in fact negative 3 sine theta. Okay, sine of 180 plus theta is in fact negative sine theta. So what we've got here is we've got negative sine theta, and on the bottom we've got minus sine theta minus 3 sine theta. So in fact we've got negative sine theta over negative 4 sine theta. Final answer is 1/4. Okay, determine the general solution of this equation. Well, we've got 2 brackets multiplying together with a product of 0. So either this bracket must be 0, so cos x must equal negative 2 sine x, right? Or sine 2x must equal a third. Sine 2x must equal 1/3. Okay, those are the 2 equations we're basically going to solve. Now, they're quite different in terms of the requirement of solving them. This first one's very straightforward because we're just going to shift sine of a third to get our reference angle or our key angle. Okay, so we're going to go, that's a little picture of a key, by the way. We're going to undo sine of a third. All right, and our calculator gives us 19,47 degrees. We want to be in quadrants 2 or 1, all right? So our quadrant 2 angle is going to be 180 minus 19,47, all right? So, and our quadrant 1 angle is going to be 19,47. So we're going to get 2x is 19,47 degrees plus 360k. All right, or 2x is 180 minus that, which is 160,53 plus 360k. Both of these can be divided through by 2 now to get x. So we get x is 9,74 plus 180k, or x is 80,27 plus 180k. All right, and somewhere on the page we must say k is an integer. Right, this one over here is quite different. We've got cos and sine in the same equation. What we're going to do is we're going to divide both sides by cos theta. So we actually get 1 equals negative 2 tan theta. Or tan theta, we divide both sides by negative 2, tan theta is negative 1/2. Right, now we're going to find our kind of key angle. All right, so we're going to shift tan of 1/2, okay, and we get a key angle here. I think it's 26. Let me just remind myself. All right, shift tan of 1/2. (26,56 degrees), 26,57 degrees. All right, and we want to be in quadrant 2, so we'd go 180 minus that. So theta would be, so it was x, and I've changed it to theta. So let me just change, I'm going to leave it at theta. 153,43 degrees. And remember, because it's tan, we can go plus 180. Okay, so there's our kind of general solutions there and these two over here. Okay. Right. Here we get asked to prove this identity. Okay. And what we're seeing here are our compound angle formulas. So really the only place we can start with this, I think, is to actually kind of expand those. So the cos of x plus y is cos x cos y minus sine x sine y. Cos of x minus y is exactly the same thing but with a plus. So it's cos x cos y plus sine x sine y. Okay, right, when we multiply this out, we get a cos squared x cos squared y and we get a minus a sine squared x sine squared y. We also get a minus sine x sine y cos x cos y and a plus cos x cos y sine x sine y. And those obviously cancel one another out. All right, so we end up with okay, cos squared x, all right, is the same as 1 minus, this is the same as 1 minus sine squared x, and this is the same as 1 minus sine squared y. And this is minus sine squared x minus sine squared y. Okay, this multiplies out to 1 minus sine squared x minus sine squared y. All right, and cos squared x cos squared y minus, sorry, this is minus sine squared x sine squared y. Right, so what we now get is we get 1 minus sine squared x plus a sine squared x sine squared y. All right, and then minus a sine squared y. And we've still got the minus sine squared x sine squared x sine squared y. Okay, just be careful about doing what I've done then. Change it times into a minus sign. Right, but in fact these cancel one another out, and now we've got our right hand side. Okay, so we've proved it. The next question says, hence determine the calculation of 1 minus sine squared 45 minus sine squared 15 without using a calculator. Now if we go back and have a look, that's basically exactly the right hand side of this thing, with 45 being our x and 15 being our y. So in fact what we've got is we've got the original thing, which is cos of x plus y times cos of x minus y. So this is all going to be equal to cos of x plus y, 45 plus 15, times by cos of x minus y, cos of 45 minus 15. All right, and this is just cos of cos of 60, and this is cos of 30. Okay, cos of 60 is a half, cos of 30 is root 3 over 2. Those are both special angles, but you can get them from your calculator, and we get root 3 over 4 is our final answer. Okay, right, let's look at this. It says, consider this trig expression. Rewrite it as a single trig ratio. Okay, well, we've got a common factor here. There's actually 8 sine x cos x in both terms. So let's factor that out. Inside our bracket, we'll have 2 cos squared x minus 1. Right. Now 2 cos squared x is actually cos of 2x. So we've now got cos 2x over here. What is this here? What's this green stuff here sort of looking like? It's sort of looking like the double angle formula for sine. Do you agree that we could write this as 4 lots of 2 lots of sine x cos x? Okay, and that is in fact sine 2x. So now what we've got is we've got 4 sine 2x cos 2x. But in fact, once again, this is kind of looking like the double angle formula for sine. So we can do it again. What we can do is we can write this as 2 lots of 2 sine 2x cos 2x. And 2 sine 2x cos 2x is just sine of 4x. So we actually get a final answer here of 2 sine 4x. Okay, and we've written it as a single trig ratio. There's no substitute for knowing your identities really well. That helps you pick these things and spot them. Then it says, for which value of x between 0 and 90 will this thing have its minimum value? And obviously the place to look is actually, what's the minimum value that sine ever has? All right, we know that. The minimum value sine ever has is at -1. Okay, now sine 4x, and we can look at the graph shortly, but sine 4x has actually had its period shortened to 90 degrees. Okay, so in other words, this value will actually be happening, all right, at 3/4 of the way along to 90 degrees. All right, and 3/4 of 90, all right, because that's half of 90, this is 3/4 of 90. 3/4 of 90 degrees, we get 67.5 degrees. Okay, that's where we'll have a minimum value. The graph that I've drawn here is the graph of 2 sine 4x. Okay, the next question is in fact about graphs. So what we're going to do is we're going to quickly just look at the trig graphs and just remind ourselves how those work. Okay, and so we're going to look at this little app over here. All right, and if, for example, we showed a sine graph, remember our cast diagram helps us draw it. It's positive in the first quadrant from 0 to 90, still positive above the x-axis from 90 to 180, and then it's negative in quadrants 3 and 4. Right, now I'm just going to work with the sine graph, but what we're going to show you here works with all the graphs. If we were to add a number at the back, in other words, instead of finding the sine of x, we worked out the sine of x plus 1. The graph would just pick up by 1. Okay, so there's sine x plus 1, and there's sine x, and there's sine x minus 1, and there's sine x minus 2. Okay, all right. vertical shift. If we were to add a number inside here, for example 30 degrees, the graph would actually move 30 degrees to the left. Okay, so the purple graph is the sort of vanilla graph. Notice that if we move a sine graph 90 degrees to the left, we actually get a cos graph. Okay, all right, so that's sine 90 plus theta, or theta plus 90. Let's put that back. If we multiply a number at the front here, in other words, instead of having sine x, we have 2 sine x, the graph just gets stretched vertically. The amplitude is being affected and the range is being affected. Obviously, if it's less than 1, it will get sort of squashed vertically. But just be aware, if it's, say, -2, here's 2, -2 will be the same sort of height, but it'll be reflected over the x-axis. There's -2. All right, and then the last one, if we put that back to sine x, if instead of drawing sine x, we draw sine 2x, it just means that we get twice as many waves in a given interval. Instead of the period now being 360 degrees, the period is now 180 degrees. Okay. All right. So there it is. Okay. Let's go back and answer some questions on trig graphs. Okay. So we've got these graphs. We've got sine 2x. Sorry. Pens seem to go a bit haywire when we change screens. Okay, we've got sine 2x. Sorry, 2 sine 2x is g, and we've got tan x. We're drawing this from -180 to 180. Right, so the first question says, what's the period of g? Right, and the period of g is, in fact, we can see it quite clearly here. It's 180 degrees. That's how long it takes to do a full wave. And it's halved because we're drawing sine 2x. So 180 degrees. Calculate the value of k. All right. And the value of k is just the value of either graph at 60 degrees. So we can choose. We can put 60 into either function. The tan of 60 is in fact the square root of 3. So k is just equal to the square root of 3. Right. Then we get asked to find the coordinates of point B. And just looking at the kind of the sort of symmetry of this thing, all right, point B, this is 60 degrees, all right, it's 30 degrees left of the asymptote. So this will be 30 degrees left of the asymptote. This point will be negative 120 degrees, and also root 3, the same value that we got for k. All right. Then we are asked, all right, for the range of twice g of x. Okay, now remember what twice g of x is going to do. It's going to take g of x, all right, and remember g of x is currently going up to 2, because there's already a 2 in front there, and down to -2. If we were to draw twice g of x, this graph would actually go up to 4 and down to -4. So our range would be -4 to 4. All right. Remember, range is all about y values. Y less than or equal to 4, greater than or equal to -4. We could write it like this as well. Y is an element of -4 to 4, both with square brackets on. Okay. All right. I have seen someone ask if we are recording the video, and the answer is yes. Okay, the next question says, for which values of x will g of x plus 5 minus f of x plus 5 be less than or equal to 0 between 0 and -90? Okay, now what I want to ask us is this a left-right shift or an up-down shift? Absolutely, it's a horizontal shift rather than a vertical shift. In fact, what this is saying is that both graphs will move 5 degrees to the left. let's look at what this is saying. It's actually saying g of x plus 5 less than or equal to, I'm going to add f of x plus 5 to both sides. Right, so it's basically saying where's g less than f? Now if we go and look right now, between 0 and negative 90, g is less than f from g, here's g, is less than f from this point here, just from the symmetry again, must be minus 60. It's less than f, as the picture stands, it's less than f between minus 60 and 0. But if we move both graphs left 5 degrees, then it'll be from minus 60 to minus 5. Okay, and we will just show a picture of that, okay, shortly. Right, then it says determine the values of x for which sine x cos x equals p. And again, this looks like our double angle formula for sine. So if we say let's make it 2 sine x cos x, all right, we would have to make that 2p, wouldn't we? All right, and then this is like saying sine 2x is 2p, but in fact the graph we've got is actually 2 sine 2x. So if we multiply both sides by 2, we get 2 sine 2x is 4p. Okay, and it's saying for which values of p, right, y equals p being a horizontal line, will we have exactly 2 roots on the intervals for which our graph's been drawn. So basically we're saying, I'm going to take out this other graph that I drew here. Okay, basically we're saying for what values of p, okay, will we get exactly 2 roots if we've got a straight line through here. Okay, our graph 2 sine 2x cutting the value y equals p. And obviously, if p is minus 2, we're going to get exactly 2 points of intersection. Or if p is plus 2, we're going to get exactly 2 points of intersection. Okay. Yeah, something's gone wrong here because, in fact, so this is 4p, all right? So I would need 4p to be plus 2 or minus 2. So 4p is plus or minus 2. So in fact, p is plus or minus a half. Okay. I'm going to show you a picture of this. Okay. There's the picture of our graphs. Okay. And we've got, let's find this picture. Right. The first question, remember, was if we move the graph 5 degrees to the left, all right, you'll just see that both graphs, everything moves 5 degrees left. Okay, so where the red graph is below the green graph, where G is below F, just moves 5 degrees. Okay, the next thing is that the P value, all right, if we make P, remember we said P must be minus a half, all right, when P is minus a half, we get only 2 points of intersection with the red graph, or when P is plus a half, we get only 2 as well. Okay, right, we have got a little way to go, still not too much. So this question over here, we've got a vertical flagpole, AB, we've got lengths as shown and angles as shown, right? So a 3-dimensional sketch. And the first thing they ask is for us to find the length of AD, this line over here, all right? And that is going to be quite straightforward because we can just use Pythagoras. Okay, it's going to be the square root of 5p all squared, plus 2p all squared, all right, and we're going to square root that. And that will be the length of AD. Right, actually it becomes 5p squared plus 4p squared, 9p squared, square rooted just 3p. Okay, so that's quite a nice sort of answer there. Right, then they ask us, and this is enough to make anyone kind of panic, they ask us to show that CD, all right, is going to equal some weird expression here. Okay, now let's just look at that expression. I suspect that expression is going to come more from the sine rule than from the cos rule. So what we're going to do is we're going to apply the sine rule in this slanted triangle on the front face here. Okay, all right. So this angle here is x, this angle here is 45. This angle in here is going to be 180 minus 45 minus x. It's actually going to be 135 minus x. All right. We're wanting to find CD. So CD over the sine of 135 minus x will be the same as AD, and remember AD we've just worked out to be 3p over the sine of x. Okay, so now if we multiply both sides by the sine of 135 minus x, we're going to get CD equals 3p sine 135 minus x, all right, over sine x. Now if we look at this, it's not all bad, okay? We've got the 3, we've got the p, we've got the sine x on the bottom, all right? We've got a compound angle formula which we can use to split up this sine 135 minus x. And in fact what it is, it's sine 135 cos x minus cos 135 sine x. All right, and this is all over sine x. Okay, so CD is in fact 3p. Now, sine of 135 is the same as sine of 45. All right, by reduction. It's 180 minus 45. So sine 145 cos x minus cos 135 is actually the same as plus cos of 45 sine x. Now the cos of 45 and the sine of 45 are 1 over root 2. Okay? So what we've got here is sine x. We've got CD is 3p. Now we've got 1 over root 2 cos x plus 1 over root 2 sine x over sine x. Okay, and we can take out the 1 over root 2 as a common factor, and we can write the root 2 on the bottom. So in other words, it becomes that, and these 1 over root 2's are gone, and that's exactly what we had to show. Okay, then it says, if it is further given that P is 10 and X is 110, calculate the area of triangle ADC. Now ADC is the same front triangle, but remember we now know CD and we know AD and we know the size of this angle. So we can use our area formula. We're going to say area is half AD times CD times the sine of 45 degrees. All right, AD, remember, AD is 3P, so it's going to be 30, 3 times 10. CD, well, there's CD there, all right. CD is going to also be 30, and there's going to be cos of 110 plus sine of 110 over root 2 sine 110, all right, times the sine of 45. Okay, so quite a hectic thing, but we can slot all of that into a calculator and we just get 143,11 units squared. Okay, right, we're moving on to some geometry now, and I'm just going to show you two sketches here. The first one is to do with angle at center. All right, let's just have a look at this sketch because I just want to show you, just make sure that you're familiar, completely comfortable with all the four different pictures here. Right, so here we've got an angle at the center, an angle at the edge. The one at the center is twice as big. This is less easy to spot when it's like that, but it still applies. It's even less easy to spot when it's like that. Some people think that's angles on the same segment. It's not. Notice the angle at the center is twice the angle at the edge. In a way, our angle at semicircle is just really almost just a special case as well. All right, but notice when we go around and we've got a reflex angle, the angle at center theorem still applies. Okay, the other one that we want to show you is this one over here, and this is the angle at center theorem, but there's another theorem kind of embedded in here as well, and let's just show you which one that is. Okay, so we've got angle at center. We drag these angles in the same segment rather. Okay, but in fact, if I make these segments bigger, the angles get bigger obviously. But even if I move one of these lines around, notice both of these angles are 41 degrees because they are coming off equal chords or equal arcs. All right, and that's really important. Okay, equal chords or equal arcs. Notice that if I change the length of the chords or the arcs, the angles stay the same even though they're both changing. Okay, right. So those are just two little theorems as to kind of as a sort of value add. Hopefully you find it useful to see the visualization of those. Right, now, and all of these visualizations that I'm using are actually available on the SIMI website. Okay, so you just go simi.education and you can go on the engage page and you can find sketches for all of these. Right, this is a fairly simple geometry question. It tells us that we've got a cyclic quad. It tells us that we've got a diameter. So this line over here is a diameter, this orange line. Okay, and we've got a radius and we've got a 64-degree angle. It says give reasons, the sizes of the following angles. Well, angle P. All right, well, angle P is in fact in a cyclic quad. All right, there's a cyclic quad basically from R to M to N to P back to R. Okay, not very well drawn. Okay, so let's just undo all of that. So angle P will be 116 degrees. One mark for that and a mark for the reason. Opposite angles of cyclic quad. Okay, angle M1. Angle M1 is this angle over here. Well, we know that SMN is 90 degrees. Angle in semicircle. All right, so if it's 90 degrees, the whole thing's 90 degrees, then M1 must be 26 degrees. O1. All right, now this is 26 rather. If we turn the diagram round, okay, if we turn the diagram round, O1 must be twice as big as S1. Right. Sorry, it's M1. Okay, so O1 must be 52 degrees. O1 must be 52 degrees. Angle at center. Okay, this next one, it says give a reason why these two lines are parallel. All right. And in fact, what we've got is that we've got this side being cut in half and this side being cut in half. So the reason these lines are parallel, all right, is the converse of the midpoint theorem. Right, the midpoint theorem says that if you draw a line parallel to one side of a triangle through the midpoint of the one side, all right, then it goes through the midpoint of the other side. The converse is if you join the midpoints of two sides of a triangle, that it's parallel to the third side. So this is the converse of the midpoint theorem. All right. Okay. Then it says, it's further given that BFC to BF is 1:4. So I'm going to call that little piece there P. I'm going to call this piece 4P just to communicate that ratio. It tells us that DE is 3x minus 1. That's an actual length. And GH is x plus 1. And it says, find, giving reasons, the value of x. Okay. Now, what we know is that this little blue triangle up at the top here is similar to the green triangle, to the bigger triangle here. These triangles are similar. And I think you can see why they're going to be similar, because we've got a common angle up at the top at A, all right, and we've got corresponding angles here, all right, and here, and then here and here. And basically, whenever we've got our proportional intercept theorem, we've also got similar triangles. Now, because, and I'm not going to write the whole thing up, but because triangle ADE is similar to triangle ABG, all right, and the reason they're similar is angle, angle, angle. I'm not going to write down those angles, okay, just to save a bit of time. Because of that, we know that AE to AG, look at that, AE to AG must be equal to DE as to BG. And that's because we've got similar triangles. Okay? But we know that AE to AG is 1:2. So 1:2 is 3x minus 1, that's DE, over BG. All right? And if we cross multiply, we actually get that BG is 6x minus 4. Okay, so BG is actually 6x minus 4. Not 6x minus 4. Was this 3x minus 2 or minus 1. This is 3x minus 1. So it's actually 6x minus 2. Okay, now let's now look in the other triangle. We've got parallel lines here and here. And we know the ratios on both sides must be equal. All right, so we now know that BF as to FC must be the same as BG as to GH. And the reason for this is the proportional intercept theorem. We know that FG is parallel to CH. Okay, so in other words, 6x minus 2 over x plus 1 must be the same as 4p over p. Right, 6x minus 2 over x plus 1. Okay, 6x minus 2 over x plus 1 must be the same as 4p over p, or just 4 over 1. And now, if we cross multiply, we get 6x minus 2 is 4x plus 4. Let's subtract 2x from both sides, sorry, 4x from both sides, giving us 2x, and add 2 to both sides. 2x is 6. We get a final answer of x equals 3. Right, that's a little trickier. Okay, on to almost, I think it's the second last question. All right, and this is some bookwork, and we've just got to prove that AD is perpendicular to AB. All right, so there's the diagram, and what we're going to do, we don't need to learn this proof off by heart. We're going to just construct the radii, okay? Going to try and draw that first one again because it was pretty ropey. Okay, so we're going to construct the radii, and we're going to try and prove these triangles congruent. Okay, and they definitely are congruent because these sides are radii. They will be equal, and then this third side is common or shared, and then obviously these two we were given as equal. Okay, so the triangles are definitely congruent. So let's write that down. Okay, so construct radii OA and OB. All right, now we know that OA is OB because they're radii. We know that AD is DB. BB, that was given. We know that OD is common. So we know that triangle AOD is similar to BOD. Not similar at all, congruent. Sorry, AOD congruent to triangle BOD. BOD. And the reason is side, side, side. Okay, and so therefore we know that angle ADO must be equal to angle BDO. All right, and that's from the congruent triangles. But ADO plus BDO is 180 degrees. Angles on a straight line. Therefore, ADO equals 90 degrees, and therefore OD is perpendicular to AB. Okay, and that's what we were kind of required to prove. Okay. All right, just going to scroll back up to the top just to show you the diagram one more time. You don't need to learn these proofs off by heart. You need to learn the strategy involved. The strategy involved is to form two triangles and prove them congruent. Okay, right, this question over here asks us to, it shows a whole lot of stuff here. It tells us that these lines are equal. All right, this is from the center. Okay, so what that does tell us, in fact, is that this is quite a tricky diagram because it's quite tight, but this must be 90 degrees. And that is the proof that we've just proved. And that's what I was speaking about earlier, about learning how the sort of thinking of the examiner works. This question's developing. We've just proved a result that now allows us to know that that angle's 90 degrees. This is a radius and this is a tangent. So in fact, this is also 90 degrees. Okay, so they ask us to prove that this shape is a cyclic quad. And in fact, it will be a cyclic quad because of these two angles. And we're going to be using converse angles in the same segment. Okay, so let's write this down. Firstly, OTG is 90 degrees. And the reason for that, okay, is line from center bisects chord. Okay, that makes it perpendicular. But also we know that OBG is 90 degrees. And the reason for that, okay, is radius perpendicular to tangent. Okay, and therefore OTG is OBG. And therefore OTBG is a cyclic quad. And the reason is converse angles, same segment. Okay, then they ask us to prove that GOB is equal to S. GOB is equal to S. Now GOB is in fact this angle over here. All right, we're talking about this orange angle over here. Now, remember what I said, even if you couldn't prove that this thing was a cyclic quad, well, it is a cyclic quad now, and as I said, it's quite tight to try and see what's going on, but GOB will actually be the same size as BTG, angles in same segment, because it is now a cyclic quad. And what do we know about angle T and angle S? Well, they are equal because they are angles on parallel lines, they are corresponding angles. Right, so let's go from where we wanted to start. Angle GOB is actually equal to angle GTB. All right, and the reason is angles same seg. Okay, but GTB is equal to angle S. And that's because they're not alternate angles, they are corresponding angles. Corresponding angles. All right, and we've got GF parallel to PS. Okay, and so therefore angle GOB is equal to angle S. Okay, and we've got one question to do, folks, the last geometry question. Right, let's take a look at it. What it tells us, we've got some parallel lines, we've got a tangent, and this angle over here, this orange angle over here, is equal to this orange angle over here. Okay, I think that's all that's written up at the top here that I need to tell you about. It tells us that there's a cyclic quad, but we can see that. Okay. It says prove giving reasons that S1 is equal to T2. Now, S1, let's just look at S1. S1 is in a strategic position, okay, because it's actually an exterior angle of a cyclic quad. So we know that S1 is equal to both of those two. All right? We also know that P1 is equal to Q1 because of the tan chord theorem. P1 equals Q1. So that equals that. Okay? And we know that T2 will be T2 is an exterior angle. Okay? I'm going to give these some names. I'm going to call this X. I'm going to call this X. I'm going to call this X. All the orange ones are X. I'm going to call Q2 Y, this little piece over here. All right. Now, what do we know about angle S1? Well, it's equal to X plus Y because it's an exterior angle of a triangle. What do we know about T2? Well, sorry, S1 is an exterior angle of a cyclic quad. T2 is an exterior angle of a triangle, so it actually also equals X plus Y. All right, let's write that down. So, let P1 let's not let P1 because we weren't given P1. Let's let R2. Let's let R2 and oh, we were given P1. Sorry, let P1 and R2 be X. But P1 is actually equal to Q1. All right, and the reason for that is tan chord. Okay, so Q1 is also equal to X. Right, we don't need a reason for that. Okay, so Q1 is also equal to X. Now, T2 is Q2 plus R2. T2 is Q2 plus R2. Actually equals X plus Y, and that's exterior angle of triangle. Okay, right. But angle S1 is equal to Q1 plus Q2, which equals X plus Y. That's exterior angle of cyclic quad. All right, and so therefore S1 equals T2. Now, again, let's just say you couldn't do that. You now need to go into part B of this question, knowing that S1 is equal to T2. All right, so I'm going to now mark that in. S1 is equal to T2. That there is equal to that there. Okay, because chances are we're going to need that. Right, now they ask us to prove this ratio. And when I look at this ratio, I'm seeing AD and ADR and ASC, or ADS and ARC. ADS and ARC. Are there possibly triangles that are similar here? Is it possible that ADS that little red stripy one, is similar to ARC, this huge green triangle over here? And I want you to look, because I think that that angle that we've just marked equal might be useful here, because that angle is in one of these triangles. Okay, but in fact, these lines are parallel. So this angle over here is T2 and C2 are equal. They are alternate angles on parallel lines. So now we've got an angle in each triangle. Okay, so those angles are equal. Okay, I'm going to write it down. I'm actually going to scroll and I'm going to write it over here. All right, in these two triangles, in triangle ACR and ASD, right, ACR and ASD. Angle A is obviously common. Angle S1, no, let's go with angle, we want to talk about angle C2 equals T2. Those are alternate angles with SQ parallel to AC. Okay, therefore C2 equals S1. I'm just going to say it from 10.1. Okay, because S1 and T2 are equal. Right, and therefore the third angle in the triangle, D1, must equal R1. Angles of triangle, and therefore the triangles are similar. Triangle ACR is similar to triangle ASD. And the reason is A. Right, so I'm just going to go down here. Triangle ACR to triangle ASD. Okay, and now we can pull ratios out. So if I take AD from here, I must take AR from this one. And then if I take AS from here, I must take AC from this one. All right, and the reason I can do that is similar triangles. Okay, not all that easy necessarily. Now the last part asks us to prove kind of something here. And if we look at it, we've got AS, and we've got TC. This is actually looking a little bit like the proportional intercept theorem. So in other words, we're now going to use the parallel lines and we're going to pull out a ratio, okay? So because if we look at it, we actually want to involve, for example, TC, which we don't have yet, and maybe let's have a look. Because from this here we know that okay. We know that RC over TC is the same as RS over RA. RS over RA. Or RT over TC is SR over SA. RT. Okay, just going to have a look at this. Okay, we know that from our similarity, we know that AC over AS is the same as CR over SD. And that's from the similar triangles that we've already proved. That actually cross multiplies to give us AC times by SD equal to AS times by CR. Okay, now if we look, the stuff on the left is what we want. The stuff on the right is AS times SR. Let's go and have a look at AS and AS times CR rather. AS and CR. So AS over SR will be, we actually want CR. So AS over AR will be CT over CR. AS over AR will equal CT over CR. Okay, I'm just going to show you that. AS over AR will be CT over CR. And that's our proportional intercept theorem with ST parallel to AC. Okay, so prop int theorem ST parallel to AC. Okay, and so we actually, if we cross multiply this, we get ASCR equals AR times CT or TC. Okay, and if we look at these two results and we combine them, all right, the right hand, this piece is the same in both. So this here is the same there and the same there. So therefore, AC times SD is equal to AR times TC. Okay, quite difficult, and probably quite difficult to follow without the diagram properly in front of you. Right, you can download this. If you look for us on social media, you can download this paper, which obviously, if you have done that beforehand, makes it a whole lot easier. Right, folks, that brings us to the end of our session. So 2¼ hours, quite hectic, but we hope that you found it useful. All right, have a great evening, everyone. Good night.